So we're going to be dealing with increasingly more complex levels of theory for how we can treat bonds. We started off looking at Lewis bond theory, where we're just basically, saying, hey, bonds have octets via CPR theory to describe the geometry of these molecules. So we're going to keep on digging into a little bit deeper levels of complexity to understand how electrons are shared in covalent bonds, particularly. So we're going to talk this time about valence bond theory. So the goal for this lecture is to understand valence bond theories, treating molecular orbitals as combinations of atomic orbitals. We're going to characterize and recognize the molecular orbitals formed from combinations of s and p orbitals as described by valence bond theory, and describe the hybrid orbitals that occur in covalent bonds using valence bond theory. So we'll be talking next time about molecular orbital theory, which is a little more complex. So this is sort of an intermediate in between Lewis theory, where we're just dealing with numbers of electrons and filled octets, and moving up in complexity, so we can understand. And each of these are sort of better and better approximations for how the electrons are arranged, and how the arrangement of the electrons changes the shapes of the molecules. Okay, so we know that the potential energy minimum of most atomic pairs is a relatively close distance. If you have, say, two hydrogens and you move them together, they actually lower the total potential energy until it gets down to about the distance of about 74 picometers. And so at that distance, what you have is a balance of the energy that you get from, if we have a hydrogen here, a hydrogen nucleus. Let's actually draw the nuclei. If you have the nuclei here and the electron cloud around it, there's a trade-off. As you get closer, the electron clouds are repelling, but also this, and then the nuclei are repelling as well, but you also have this electron cloud attracting this nuclei, and this electron cloud attracting this nucleus. And so there's a lot of very complex behavior that's happening. And it turns out that at a certain distance, you get the minimum possible energy. You get any closer than that, and the nuclear repulsion starts to overpower the total energy. So it's not at all clear exactly where that trade-off is, and you have to do a lot of fancy calculations to figure it out. But generally, as atoms approach each other, you get lower and lower energy. So the question is, what are the electrons doing when atoms are this close to lower the energy so much? Valence bond theory says, well, it's a quantum mechanical model. It's an approximation to the true Schrodinger's equation, but tackled at sort of a qualitative level, which describes how electron pairs and atomic orbitals are shared in a covalent bond. So covalent bonds are formed by orbital overlap. The molecular orbitals you assume are sort of combinations of the atomic orbitals the atoms came in. Now, this is not entirely correct, but it's roughly right. So electrons involved in overlapping orbitals are shared. So if you have overlapping orbitals, then the electrons are shared between those two orbitals. The more overlap, the stronger bond. It's not quite as accurate or general as molecular orbital theory, and we'll get into that next. So again, the interaction energy is usually stabilizing. So it's usually stabilizing when interacting atomic orbitals contain a total of 2 electrons that can spin pair, orient with opposing spins. So for example, in the simplest case, when you have 2 hydrogens, now they each have 1 electron because they've got 1 proton, and you notice that if you share the orbitals together, if the orbitals come together, then you essentially have a single molecular orbital that can have both a spin up and a spin down, because this requirement that you can, any orbital can only have a maximum of 2 spins, 1 up and 1 down, 2 electrons, 1 spin up and 1 spin down, holds in all these levels of theory. You can't get away from that. So, and this is called a sigma bond. And originally the name came from the fact that you're forming them from s orbitals, though as discovered, you can form them in other situations as well. But if you have this head-to-head overlap of orbitals, and that these new orbitals that are formed, in this case, you can fit those 2 electrons into this new orbital, forming a sigma bond between the hydrogens. This applies in other situations as well. Let's imagine that you have a hydrogen, you've got a 1s orbital, and then a fluorine with 5 2p electrons. So you notice that there's an extra there's a place in its orbital for an extra electron. Again, with hydrogen, with its 1s orbital, it has a place for electron as well. And so you can imagine, and it's a relatively good approximation, that you have a new orbital formed by the combination of the 2p orbital orienting in that direction. And again, it doesn't really matter which direction, x, y, or z. They're symmetric. You have an orbital combination of those two. So you have the 2py and the 2pz that don't really participate very much. But what it is it's one, in this case, the px is interacting with the 1s orbital, combining to form a new orbital. And now in this new orbital, it's sharing those electrons. You do have a spin pairing of up and down. And now fluorine has its filled p orbitals and hydrogen has its filled 1s orbital. So that is how a valence bond theory works in that case. Again, this is moving beyond the Lewis theory because we're actually dealing with locations of orbitals in space rather than just counting octet rule. Okay, yeah, so that's a new sigma bond that we formed there. If you have two fluorines, we know that fluorines combine to form F2. This would be applicable to any halogen. Let's just start with fluorine. You've got, each of them has 5 2p electrons. So you can imagine a shared orbital, that the px's, it shares the px's, and together that new bond, which is also a sigma bond formed by this head-on interaction of p orbitals, is filled. You've got the px, py, and pz that are sort of independent, and then the px that are not participating in the bonding, but the px's form this new orbital, this molecular orbital, which forms a sigma bond, and then all of the orbitals are filled. And so that's the basic idea of valence bond theory in terms of sharing orbitals. You can generalize this a little more. A hydrogen sulfide, the sulfur atom has, it has three electrons, 2 3s electrons and 4 3p electrons. So it's missing 2 electrons in order to fill those orbitals. So you can imagine that hydrogen can donate that 1s electron, create 2 new orbitals. Now with 2 of the p orbitals, 1 p orbital stays out of it, it's already full, but the other 2 p orbitals donate their electrons as well, and you get something like this. Because 2 of the p orbitals are not involved, then you would have 2 H atoms forming about a 90-degree bond between them. And again, these are approximations to Schrödinger's equation, but this ends up being a pretty good description of what's happening in hydrogen sulfide. We can look at some of the other things like hydrogen sulfide, hydrogen selenide. Selenium is 1 below sulfur, or phosphine, pH 3, arsenine, and you get something that looks very much like this. Here, a hydrogen sulfide, you have a bond angle of about 90 degrees, indicating that the fact that the bonds are formed between a combination of a p orbital, a p orbital on the sulfur and an 1s orbital on the hydrogen is a good approximation. Same with hydrogen selenide. Phosphine, remember phosphine, it has it's the analog of nitrogen one further. So if you look at its 4p electrons, we've got 3 4p electrons. So there's the 4p electrons. Remember it has 5 valence electrons. The 4s are spin up, spin down, those are filled. And then it has 3 empty, 3 p orbitals that are only half filled. So it can accept 1s electron from each of the, if you have 3 hydrogens, each of which have a 1s electron, from hydrogen 1, hydrogen 2, hydrogen 3, those combine, and you get 3 orbitals formed by the px, the py, and pz. And so these are, again, relatively good descriptions. As you can see, as you actually go down to heavier metals, it becomes, not metals, they have a little more metallic character, heavier atoms, that it does get closer and closer to that 90-degree angle between all of the atoms. So that's cool that in many cases you can describe the covalent bonds just as combinations of atomic orbitals.